Alright, this is the video for 10.7. We are going to go ahead now and look at the kinetic molecular theory of gases and look at now the relationship between pressure and volume, pressure and temperature, volume and temperature, and all the other ones and see why those happen. And like I've said a lot this chapter, we did this last year, so it should be hopefully a quick little review on what we did then. Alright, there are four postulates of the kinetic molecular theory, or KMT, and the first one is that particles are so small compared to the distance between them that the volume of particles themselves is negligible. This means that they are so tiny compared to the big space that it takes up, that the little bitty space that that particle takes up doesn't make any difference. The second one is that particles are all in constant motion and that at collision with the wall, that is my pressure. Alright, the third one here is that the particles do not exert a force on each other. There's no attractions or repulsions between particles. The fourth one is that my average kinetic energy is proportional to the temperature in kelvins. So these are the four postulates of the kinetic molecular theory that we're going to look at, which are kind of the ideas behind an ideal gas, or what constitutes as an ideal gas. Because if it is an ideal gas, it follows these four postulates of this theory. Okay, so now let's look at pressure and volume, which is Boyle's law, and why these interactions occur. Okay, so if we talk about pressure and volume, if I have a container, and I'm going to change it to another container, okay, if I take this container with my gas particles in it, and I am going to decrease my volume, okay, so volume is going to go down. As the volume goes down to a smaller size, now these particles that I had originally are closer together because they have less space. Well, if they have less space to move around in, they're going to collide more. So as my volume goes down, my pressure goes up because there are more collisions between the particles and the container wall. Okay, so that's pressure and volume, inversely related. The next one is pressure and temperature. So if I have my vial here to start out with, I've got my gas particles. Okay, I'm going to take and I'm going to heat it up. So here's my temperature, my Bunsen burner flame. I'm going to heat it up so my temperature goes up. Okay, as my temperature goes up, my volume of my container stays the same. Well, as the temperature goes up, these particles are going to start moving a lot faster. And as they move a lot faster, okay, so if I could kind of zoom in on them, you'd see more of these little particles with these really, like we'll call whoosh lines behind them, where they're moving a lot faster. Okay, here they have less lines behind them. They're not moving quite as fast. They're a little slower. So my temperature goes up. They start moving more, which means that they are going to collide more. So the particles start to move faster, collide more, have more pressure. So as my temperature goes up, my pressure goes up. That's pressure and temperature. The next one is volume and temperature, which is Charles's law. Okay, I've got one container to another. I'm going to take again and heat my container up, so my temperature is going to go up. I have these little particles here. I'm going to heat them up. Okay, again, they're going to start to move faster, so I'm going to move faster. Or just like I said a second ago, they're going to move faster, which means my pressure is going to want to go up. But since it's not one of these two things that I'm looking at, I have to keep my pressure the same. So in order to keep the pressure the same, my volume has to then increase to relieve that pressure. So now I've got my container that's going to have a larger volume. Volume goes up, temperature goes up. Okay, look at the next one. We have volume and number of moles. This is Avogadro's law. Okay, so if I take my container and I start with a certain volume and I have these amount of moles, and I'm going to take and I'm going to add more of them in there. So now I've got lots more particles, lots more moles. Okay, so more moles. And when we look at moles, we have the N. So N's going to go up. Okay, well, as my moles increase, that means my pressure is going to increase because there's going to be more collisions because there's more of them. Well, I don't want my pressure to go up, so in order to relieve that pressure, my volume has to go up. So my volume goes up as amount goes up. That is volume and amount. The last one is with mixtures of gases. Okay, this is what we call Dalton's Law. And we looked at this already. So the pressure total equals the pressure of 1 plus the pressure of 2 plus the pressure of 3, or however many you have. Okay, this works because the gases don't interact. And this is just like we said in the kinetic molecular theory. The gases do not interact. Okay, the next thing here is with the meaning of temperature. Okay, so it can be seen from the KMT that Kelvin temperature indicates the average kinetic energy of my particles. And the exact relationship is actually combining a couple of equations. And it's actually a very important relationship because it summarizes the meaning of the Kelvin temperature of a gas. Okay, and as my higher temperature goes up, I'm going to have more motion. So my kinetic energy is equal to 3/2 RT. And in this case, though, the R is not our normal R value because we're dealing with energy, so I need something in joules. So my R is going to be 8.3145 joules per mole Kelvin. This R is also on the green sheet, it's just a different R, so be very careful with the units here on which R you are using. Let's try a practice problem here. Calculate the average kinetic energy of CH4 and N2 molecules at 273 Kelvin and 546 Kelvin. Now it doesn't matter what it is because that kinetic energy equation, okay, is not based on what it is. So I don't care what it is, it's going to be the same. All I care about are my temperature. So I'm going to have two parts here. The kinetic energy at 273 Kelvin and then my kinetic energy at 546 Kelvin. So since it's 3/2 RT, I take 3/2 times my new R is 8.314 times 273, and I'm going to get an answer of 3404.79 joules per mole. Okay, and it wants the average energy per molecule and not per mole, because it talks about these molecules. So I wanted it per molecule, then I would just take and divide by my 6.02 times 10 to the 23rd, which is how many molecules are in 1 mole, and we get 5.66 times 10 to the negative 21st joules for every molecule of either CH4 or N2. Same thing will go for the next one. We've got 3/2 times 8.314 times my temperature, which is 546. I get my answer of 6,809.58, and that's joules per mole. To get it per molecule, you divide by 6.02 times 10 to the 23rd, because that's how many molecules are in 1 mole. If you don't like dividing, again, you can set up a ratio, but my answer is going to be 1.13 times 10 to the negative 20th joules per molecule. Okay, another thing with kind of temperature and movement is what we call root mean square velocity. And root mean square velocity is the average velocity of the gas particles. And it's actually the average of the squares of the particle velocities, which is why it's called root mean square. It's these mean, the average of the squares. Okay. It's often denoted as U with a little line, K squared, and the root mean square is the root of that, which is a square root of this mean square velocity. And it's often written as RMS, root mean square. Okay. The root mean square velocity is square root of 3RT over m. So if you want to figure out the average velocity of these particles, in essence, this is what I'm going to do. Now be careful with this m. M is molar mass, but this has to be molar mass in kilograms because this is my R that deals with joules, and joules and kilograms. Joules have kilograms in that particular unit. A joule is not a unit that's just a joule. Joules stand for, I believe it's a kilogram times a meter per second squared. Okay. So let's try a couple practice problems here. Calculate the root mean square velocity for the atoms in a sample of helium gas at 25 degrees Celsius. So root mean square is just 3RT over m, the square root. So 3 times R, and it has to be the R with 8.314 because that's all the joules in it, okay, times 298, all over my molar mass in kilograms. My molar mass of helium is normally 4 grams per mole. So in kilograms, that's 0.004 kilograms per mole. So I multiply and then divide, take the square root, and we get 1,360 meters per second. Try the next one. And you calculate the root mean square velocity for nitrogen. Only thing that's changing here is my mass, and I'm going to have 515 meters per second. Okay, in conclusion here, it says to consider a 1 liter container of neon gas at STP, where STP is standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius and 1 atmosphere. And it wants to know, will the average kinetic energy, and frequency of collisions of gas molecules with the wall of the container increase, decrease, or remain the same under each of the following conditions. Okay, if I take my temperature and I increase it to 100 degrees, my kinetic energy is going to go up because I'm going to be moving faster. My frequency of collisions is going to go up. Well, if my kinetic energy goes up, obviously my velocity is going to go up. Okay? My temperature is decreased. The exact opposite is going to happen. My kinetic energy is going to go down. My velocity is going to go down. I'm going to be moving a lot slower. Which means my frequency of collisions is going to go down. Now my volume is decreased to half a liter. That has nothing to do with my kinetic energy and how fast something's moving, so it stays the same. My velocity stays the same. But my frequency of collisions goes way up. Because they're going to be colliding more. It's a smaller container. My number of moles of neon is doubled. Well, again, that has nothing to do with my kinetic energy or my velocity. They stay the same. Whereas my frequency is going to go way up because I have way more collisions.